For many decades, the most commonly used motor for industrial applications was the three-phase squirrel cage induction motor. These widely used devices are available in horsepower ratings ranging from a fraction of a horse to several hundred horsepower. They are reliable, efficient, and cost much less to operate than did the older DC motors. However, in the beginning of the servo system era, these mighty workhorses could not be used. Within the past 2 decades, research and development has brought about the revolution of the AC servo drive. Internally, the AC servo drive contains a rectifier circuit to convert the AC power into DC power, a DC to DC filter or link circuit, and an inverter circuit to invert the DC back to a controlled AC source of power. Now let's examine these circuits and see how they work. We will begin with the rectifier circuit. Here you see a single-phase, full-wave bridge rectifier circuit consisting of 4 diodes, a load resistor labeled RL, and a 60 Hz single-phase source of power. Notice in this illustration, we have made the top of the power source positive and the bottom negative. The current leaves the negative terminal of the power source, flows through diode D3, through the load, through diode D4, and back to the positive side of the power source. Now we have reversed the polarity of the power source, making the top negative and the bottom of the power source positive. As you can see, the current now flows from the top of the power source through diode D1, through the load resistor labeled RL, through diode D2, and back to the positive side of the power source. In actual operation, the diodes switch in pairs. One diode allows the current to flow into the load resistor, and the other diode allows the current to flow back to the source of power. Even though the diodes are switching, the current continues to flow in one direction through the load. Thus, a DC or direct current is developed. Most single-phase AC servo systems will use a full-wave rectifier like the one being illustrated here. Now let's examine the three-phase full-wave rectifier circuit. Notice that it consists of 6 diodes labeled D1 through D6. As before, we have added a load resistor labeled RL to complete the circuit from one leg of the power source to one of the others. Now let's see how this circuit functions. We will begin with incoming leg X1 at phase angle 0. At this phase angle, leg X2 is already 240 degrees into its cycle. This places it in the negative portion of its cycle. Leg X3 is at 120 degrees in its cycle and is therefore positive. As you can see, the current flow is now from leg X2 through diode D5, through the load resistor, and then the current splits and returns through diodes D1 and D3. Now we have incremented leg X1 by 45 degrees. Notice that the polarity on the diodes has not changed. Therefore, the current path remains the same in this position of the three-phase cycle. Even though the polarity of the diodes did not change, X2 is now at 285 degrees in its cycle, and leg X3 is at 165 degrees. Now we've advanced to the 90-degree point for leg X1. Notice that leg X2 has advanced to 330 degrees, which makes it a negative voltage, and leg X3 has advanced to 210 degrees, which also places it at a negative potential. The current now flows from legs X2 and X3 through diodes D4 and D5, through the load resistor RL, through diode D3, and back to leg X1 of the power source. When leg X1 reaches 135 degrees, leg X2 swings positive with a phase angle of 15 degrees, and leg X3 remains negative at 255 degrees. This allows the current to flow from leg X3 through diode D4, through the load resistor, through diodes D2 and D3, and back to legs X1 and X2. At 180 degrees, leg X1 begins its negative swing. Leg X2 is positive at 60 degrees, and leg X3 is still negative at 300 degrees. Now notice that the current flows from legs X1 and X3 through diodes D4 and D6, through the load resistor RL, and returns to leg X2 through diode D2. When leg X1 reaches 225 degrees, leg X2 is positive at 105 degrees, and leg X3 is negative at 345 degrees. Even though the phase angle on the three phases advanced 45 degrees, the current path remains the same through the rectifier circuit. At 270 degrees, leg X1 is still negative, leg X2 is still positive at 150 degrees, and leg X3 swings positive with a phase angle of 30 degrees. The current now flows from leg X1 through diode D6 through the load and returns to legs X2 and X3 through diodes D1 and D2. In the final portion of the three-phase cycle, leg X1 is negative at 315 degrees, leg X2 is negative at 195 degrees, and leg X3 is positive at 75 degrees. This allows the current to flow from legs X1 and X2 through diodes D5 and D6, through resistor RL, through diode D1, and back to the positive terminal of incoming line X3. As you can see, three-phase voltages placed at 120 degrees phase shifts can be used to produce a direct current potential. Notice that the current continues to flow in the same direction through the load resistor, just like it did in the single-phase rectifier you examined a moment ago. Also notice that the top three diodes are used to allow the current to return to the source of power, whereas the bottom three diodes are simply used to supply the current to the system. You might also have noticed that only half of the diodes are turned on at any given point in the three-phase cycle. Now that you have an understanding of single-phase and three-phase rectification, let's examine the DC to DC link section of the AC servo system. The DC link is nothing more than a filter circuit composed of iron core inductors and/or capacitors. As you should recall from your motor theory, anytime a current is passed through a coil, a magnetic field is generated. When this magnetic field expands and cuts through an adjacent wire, it induces a voltage into the wire. This voltage is such that it will oppose the force creating it, and is thus called a counter-electromotive force. It is this counter-electromotive force that allows the coil to reduce any variations in the incoming voltage. The capacitor, on the other hand, works like a storage cell. As the voltage applied to the capacitor increases, it causes the capacitor to charge. When the voltage begins to decrease, the capacitor releases the stored voltage back into the circuit, thereby causing the voltage to remain constant. Here you see the converter and DC link portion of an AC servo system. The DC link in this circuit consists of two iron core coils and one capacitor. Notice that the output voltage from the three-phase rectifier circuit is actually a pulsating DC and not a pure or flat DC. By passing the current from the converter circuit through the coils, the pulsating direct current is greatly reduced. The capacitor on the inverter side of this circuit removes any fluctuations in the current that might be present. As you can see, the operation of the DC link circuit is not that difficult to understand. Next, we will examine the heart of the AC servo system, the inverter. The primary function of the inverter stage is to invert the DC voltage into a pulsating DC voltage whose frequency can be controlled. The output voltage from the inverter stage will closely resemble an AC signal. However, the one notable difference is that the voltage will never actually swing negative. Instead, it swings from a low positive potential to a high positive potential at a controlled rate. Some of the newer AC servo controllers have inverter stages that can reach frequencies of 15,000 Hertz. AC motors operate on a principle of electromagnetic induction from a source of power which varies in magnitude. The frequency being fed into the motor actually determines, to a great extent, the speed at which the motor will operate. If you can make the circulating magnetic field being generated within the motor windings go faster, the armature will turn faster to keep up with the faster moving magnetic field. In the same respect, By reducing the speed of the circulating magnetic field, you can actually make the motor run slower. Therefore, by controlling the frequency being fed into an AC motor, you can easily speed up the motor by increasing the frequency, or you can slow it down by decreasing the frequency being applied to the motor windings. Basically, this is what the inverter circuit does. There are other circuit parameters involved in the control of an AC motor. We will examine these in a moment. But first, let's examine the inverter circuitry to see how it produces a pulsating signal that can be varied in frequency. Here you see a typical inverter control circuit. As you can see, this control system is somewhat more complex than is the typical DC servo controller. Notice that it contains the feedback and summing junction like those used in the DC servo control system. This portion of the control circuit is almost identical to those used in DC drives. The inverter control circuit also contains a variable frequency oscillator. The output frequency of the oscillator is controlled by the error signal coming from the summing circuitry. The higher the error voltage, the higher the frequency from this circuit will become. Notice the phase shift circuitry. In a single-phase AC servo controller, this phase control circuitry is not required. However, the three-phase system must have its voltages phase shifted by 120 degrees from one another to imitate the actions of a standard three-phase voltage system. The inverter control circuit also contains three fire control stages. Notice that the top fire control circuit is not phase shifted, whereas the other two are phase shifted 120 degrees and 240 degrees respectively. This places the output voltages at the proper 120 degree phase shift necessary for proper three-phase motor operation. Finally, the fire control circuits feed into the switching circuits, which are used to control the electrical energy being fed into the three-phase motor. These devices are generally insulated base bipolar junction transistors. Bipolar devices are typically used due to their extremely fast switching speeds. In actual operation, the tach feedback signal and command signal are summed in the usual manner. The signal from the tach generator is fed into the inverting input of an operational amplifier. The signal is then algebraically summed with the command signal, therefore providing the error signal. The error signal is then passed through an amplifier stage and fed into the variable frequency oscillator stage. The oscillator then outputs a series of pulses proportional to the incoming error signal into the two phase shift stages and one fire control stage. The signal going into the fire control circuit from the variable frequency oscillator must first pass through a delay circuit contained in the oscillator circuitry. This delay circuit is necessary due to the processing time of the phase shift networks. The phase shifted signals are then fed into the other two fire control circuits. Since the fire control circuits are now timed properly, they turn on and turn off the bipolar power semiconductors in the switching circuitry. This power is then fed into the three-phase motor to make the motor run. As the rotor in the motor turns, the tach generator also rotates, thereby closing the loop in the servo control system. Notice that the power semiconductors are operated on a direct current power source. Therefore, the motor is actually operating from a pulsating DC and not a true alternating current. However, the windings in the motor cannot distinguish the difference between the pulsating DC and the standard AC it was designed to operate from. Next, we will examine some common inverter circuits. You just saw how controlling the frequency of an AC motor can be used to regulate the speed of the AC motor. However, controlling only the frequency of the AC power being fed into the motor will not allow full control of the motor's speed. The voltage must also be controlled. For an AC drive to function properly, the voltage to Hertz ratio must be maintained. This means that if a motor shaft rotates at 3450 RPM with a 60 cycle 440 volt incoming power source, the voltage and frequency would both need to be reduced proportionally to reduce the speed of the motor. At a 50% speed rate, the voltage would have to be 220 volts and the frequency would have to be 30 Hertz. There are three common methods used to vary the incoming voltage. One uses SCRs in the converter circuit, another utilizes a chopper circuit, and the third system uses the pulse width modulation technique. Here you see a variable voltage inverter circuit using SCRs in the converter stage. The frequency control portion of the circuitry still varies the frequency of the output voltage being fed into the motor windings. The feedback control is the same as those you have already examined. Notice the addition of the SCR control section. Using SCRs in the converter stage allows the controller to dictate when an SCR is turned on and how long it will conduct. If the SCR is turned on early in the cycle, it will produce a higher potential for the DC link circuit. In the same respect, if the SCR is turned on late in the cycle, it will produce a lower voltage potential into the DC link circuit. By controlling the turn-on time of each SCR in the rectifier circuit, the voltage being fed into the DC link and inverter circuit can easily be controlled. Notice that the feedback control circuitry feeds the error signal into both the SCR control circuit and the frequency control circuit. In doing so, the error signal is capable of controlling both the voltage being fed into the inverter circuitry as well as the frequency of the pulsating DC signal being fed into the motor windings. As the frequency increases, so does the voltage output from the converter stage. In the same respect, when the command signal swings to a lower potential, the voltage produced by the converter circuit drops accordingly, and the frequency from the frequency control circuit decreases. As was stated previously, the voltage to frequency ratio must remain constant for total control of the AC motor. Next, we will examine the chopper circuit. Here you see another version of the variable voltage inverter circuit. Due to its constant supply of DC voltage from the converter circuit, this system is also commonly referred to as a voltage source inverter. This control system contains feedback circuitry, frequency control circuitry, a full-wave three-phase rectifier using diodes, switching circuitry, and a chopper control circuit utilizing an insulated gate MOSFET device with a capacitor. You should have noticed that this circuit looks very similar to the SCR-controlled system you just examined. Now let's see how this circuit is able to control the DC voltage being fed into the inverter circuitry. The operation of the chopper circuit is quite easy to understand. The MOSFET device placed in series with the DC power source functions as a switch. When the MOSFET transistor is turned on, the current flows through the inverter circuitry and into the capacitor. As the current flows into the capacitor, it becomes charged with the power supply's potential. When the MOSFET transistor turns off, the charge on the capacitor begins to discharge through the inverter circuitry and back to itself. Now let's see how the chopper-controlled inverter actually functions. Here you see the chopper control system in operation. The incoming three-phase power is first fed through a full-wave rectifier circuit consisting of the 6 diodes. The pulsating DC potential is then filtered by the 2 coils and the first capacitor. The flat DC signal is then chopped at a fixed frequency by the chopper control circuit. However, the on-time duration and off-time duration of the MOSFET switching device is controlled by the error signal coming from the feedback control circuitry. If the chopper control circuit is operating at a fixed frequency of 10,000 Hz and the drive is being controlled to operate the motor at a 50% speed rate, then the MOSFET switching device will conduct for 5,000 pulses and turn off for the other 5,000 pulses. Each time the switching transistor turns on, its capacitor begins to charge to the DC potential. When the switching transistor turns off, the capacitor discharges through the inverter circuitry and back to itself. As you can begin to see, by controlling the on duration and off duration of the chopper transistor, it is easy to control the amount of voltage allowed into the inverter circuitry. As in the previous circuit, when the command signal increases, the output frequency of the frequency control stage increases and the switching transistor remains on for a longer duration of its cycle. When the command signal decreases, the frequency control stage lowers its output frequency and the on time of the MOSFET switching transistor becomes shorter, thereby causing the average DC voltage being supplied to the inverter circuit to decrease. Next, we will examine the pulse width modulated control system. The AC variable voltage pulse width modulated inverter control system is very similar in operation to the DC pulse width modulated system you examined in Part 5 of your servo control training. With the exception of the control circuitry used to maintain the voltage to frequency ratio, the circuits are almost identical. As you can see, The pulse-width modulated AC servo control system uses amplifiers, inverters, a comparator stage, ramp generator circuitry, a variable frequency control circuit, and a fire control stage for the power pack. Also shown is the three-phase rectifier, DC link, and voltage control sections. Now let's see how this system works. The feedback signal from the TAC circuit is fed into the non-inverting input of the first buffer amplifier stage. From here, the signal is routed into the inverting input of the second buffer amplifier stage. This stage is labeled INV to indicate that the signal is inverted. As you should recall, it is necessary to invert the feedback signal so the command and feedback signals will subtract from one another and not add together. Next, the output from the second buffer amplifier stage is split and fed into a third buffer amplifier being used as an inverter circuit, and into the summing junction with the command signal. Notice that the command signal and the inverted feedback signal combine and flow into the non-inverting input of the comparator circuit. The purpose of the second inverter stage is to invert the negative signal back to a positive signal to be used by the variable frequency control circuit. Now notice that the ramp signal, which typically operates at 2000 to 5000 Hz, and the error signal, which is a DC signal, are both fed into the comparator circuit. When the ramp signal equals or exceeds the error signal potential, the output of the comparator stage turns off. As you should recall, the comparator operates in one of two modes, cutoff or full saturation. While the comparator is operating in its saturation mode, the MOSFET transistor is turned on, allowing the capacitor to charge. When the comparator turns off, the MOSFET device also turns off. Also notice that the error signal is inverted and then used to control the frequency of the variable frequency control circuit. Here you see the circuit in full operation. Notice that as the command signal increases or decreases, the output of the comparator stage follows proportionally. Since the comparator IC is only pulsed on for specific portions of each cycle, its output will produce a pulse width that is in direct relationship to the error signal and ramp generator signal being fed into it. When the command signal is low, the feedback signal will also be low, resulting in the frequency control circuitry producing a lower frequency output. In the same respect, when the command signal is high, the feedback voltage will also be high, thereby causing the frequency control circuitry to produce a higher frequency signal. As you can see, this circuit is capable of controlling both the frequency and voltage being fed into the AC motor windings. If the DC supply coming from the converter DC link stages has a maximum voltage of 100 volts and the frequency control oscillator has a maximum frequency of 10,000 Hz, then the voltage would have to be dropped to 50 volts and the frequency dropped to 5,000 Hz to operate the motor at a 50% speed rate. Always remember, the voltage to frequency ratio must always be maintained for proper AC motor operation. The primary difference between the pulse width modulated system shown here and the chopper circuit just discussed is that the series connected MOSFET transistor is operated in one of two modes. It is either at full saturation or at cutoff. The pulse width modulated MOSFET device is not fed with a fixed frequency like the chopper transistor was. Therefore, the DC being fed into the power switching circuitry is not chopped at a high frequency. It is merely controlled. Next, we will examine the current source inverter system. The current source inverter is an AC drive which monitors and controls the current while varying the frequency fed into the AC motor windings. Current source inverters are controlled using one of two common methods. One method involves the use of phase controlling the turn-on time of SCRs in the converter circuit, and the other method utilizes chopper circuitry. The primary difference between the voltage-controlled and current-controlled systems are the large inductors used in the DC link stage and the current feedback and control circuitry. You might also notice that capacitors are not used in the DC link stage when the current is being controlled. The feedback device most commonly used for monitoring the motor current are coils of wire wound around the leads going to the motor windings. As the current flows through the motor leads, it generates an electromagnetic field. This electromagnetic field cuts through the coils of wire wound around the motor leads and induces a voltage of its own into the coils. This voltage is then fed into the current control circuitry to be timed, shaped, and then combined with the error signal. The The current control circuitry will typically contain buffer amplifiers and current limiter circuits for each current feedback signal. The second buffer amplifier in each string is generally used to invert the feedback signal. These signals are then combined to form an average current signal strength and then summed with the error signal from the tach feedback and command signal to produce a new error signal inside the feedback control circuitry. As you can see, the current source inverter system is somewhat more complex than are the voltage-controlled systems. Now let's see how the SCR current source inverter control system works. When the servo is in operation, the command signal is summed with the tach feedback signal and then with the current feedback signal. An error signal is then produced and fed into the SCR converter control section and into the insulated base bipolar junction transistor control circuitry. By varying the firing angle of the SCRs, we can cause the SCRs to fire later in the AC cycle or earlier in the AC cycle. When they fire early in the cycle, the average output current becomes higher. When they are fired later in the AC cycle, the average output current becomes lower. The controlled DC current is then fed through the large inductors used in the DC link section. The operating characteristics of the inductors allow it to produce a constant current into the inverter circuitry. The inverter then controls the switching time of the insulated base transistors, thereby controlling the current flow through the motor windings. Through the use of the current control circuitry, this control configuration is capable of monitoring and controlling the current flow through the motor windings. The voltage being developed for the motor windings is dependent upon the impedance of the motor windings and the load on the motor. Now you see the pulse width modulated current source inverter. Notice that it looks very similar to the circuit just examined. The PWM current source inverter contains the same current control circuitry, current feedback circuitry, and large inductors in the DC link stage. It also contains a chopper control stage, a MOSFET switching transistor, and a ramp generator used to control the chopper action. As with the previous chopper circuits, the chopper operates at a fixed frequency that is typically 2000 to 5000 Hertz. The on-time and off-time duration of the chopper transistor is controlled, thereby allowing control of the current flow from the converter circuit into the DC link and inverter circuit. In operation, the chopper circuit controls the amount of current being fed into the inverter circuitry. The longer the on-time duration of the chopper transistor, the higher the average current value will be. Since the feedback circuitry is designed to monitor and control the current being fed into the motor windings, the voltage produced by the chopper action will be dependent upon the impedance of the motor windings and the load applied to the motor. As with all AC servo control systems, the frequency fed into the inverter circuitry will be controlled by the error signal from the feedback circuitry. The lower the error voltage, the lower the inverter output frequency becomes. As you can begin to see, voltage variable controllers are designed to monitor and control the voltage of the motor windings. The current is allowed to fluctuate to meet the demands of the motor. The current controller, on the other hand, is designed to monitor and control the current flow through the motor windings, leaving the voltage to fluctuate, thereby meeting the demands of the motor. This concludes video lesson 6. At this time, you should stop the video and complete part 6 in your study guide.